Alright, in this video we're going to go over lots of examples of hash functions. So we're going to start with the one that we already did, just as a little warm-up. So this is the Annabrew company that produces car parts, and the parts are numbered with first an uppercase letter and then 4 digits. So the first question is, how many different part numbers are there? So remember, we found this because we know that the first digit can be any one of the capital letters, so there's 26, and then we multiply it by all the combinations of the last 4 digits. So because there's 4 digits, that means that there's 10,000 combinations. And so when you work that out, you can get 260,000 different combinations. We also went ahead and wrote this hash function, and so as a reminder of how this hash function works, it starts by binning. So we basically bin the array into the A's and then the B's, and what we do is, and then all the way down to the Z's, which is going to be the 25th bin. We calculate the bin, so A is 0, B is 1, Z is going to be 25, and so we can calculate that bin by simply taking the part number, the letter that starts off the part number, which is in the first index of the string, and then subtracting off the A character, and that will give, A to 0, B to 1. Then we're going to erase the letter and the dash out of the part number, and then from there we can finish off getting the rest of the bins. So the first thing is we need to convert the rest of the part number, so all that's left is the 4 digits. So we're going to convert the rest of it to an integer using stoi. And then in order to, get A000, all of these numbers into this bin, we basically will just return the bin multiplied by 10,000. So that will get us here or here or here. It'll get us the top of any bin, and then we add in the offset, which is how it's going to determine, where inside of the bin to go. So that's how this hash function works. This is a perfect hash function where there is a one-to-one relationship between the part number and the actual index that it goes into in the array. So let's look at a bunch of other different ways to do this. So the first one is hashing a UIN. So a UIN has 9 digits, but we're going to take in an additional piece of information, which is that the first digit is always 6. So the pattern becomes 6 with 8 X's. So how big of an array do you need to cover all possible UINs with this particular hash function? So the hash function is simply going to subtract off 600 million, and that will get you a unique index for every UIN. So the way to think about it, and I think it just takes some convincing when you first start doing these, is that you have 8 digits, which means you're going to have 100 million possibilities. And remember, you get that from just writing it out. So with 8 digits, you're starting at 0, and then you'll go to 1, and then you'll go all the way to all 9s and all the digits. And so if you have that many, that's going to be equivalent to 100 million possible elements in your array. So let's look at how we might hash a phone number. So at UIC, phone numbers start with the Chicago area code, and then there's a 3-digit prefix, and at UIC the 3 prefix options are 355, 413, and 996. So given a phone number, you can guarantee that the first area code is 312, and then there's only those 3 prefixes. So here's a potential hash function, and the question is, is this a good hash function? So this hash function is going to break it up into the 3 switch cases for each of the prefixes, and then it kind of bins the last 3 based off of those 3 possible options. So let's try it out. So I'm going to give you this phone number, 355-0002, and then let's try 413-0001. If you hash this into the hash function, it's going to come out with just the last 4, which is going to be 2. And then if you hash this in, it's going to be double the last 4, so this is also going to hash to 2. So as you can see with this example, there would be lots and lots of different collisions that you might have from this hash function. So let's try another one. So for this one, our hash function is going to do the same binning that we did in the previous question. So in this case, we are going to take the so let's try Professor Reed. So we are going to take and multiply the prefix by 10,000 and then add the last 4, which is going to be 9478. So what's going to happen with this is that this will be unique. So there'll be no collisions, but there'll be mostly empty elements in the array, right? Because we're creating bins for all prefixes, regardless of whether or not they would potentially be used. And we already know that there's only these 3 prefix options. And so a lot larger than necessary for this hash function. So let's look at one more type of hash function. This one will be with a net ID. And so you kind of understand this idea of binning. So you basically just take whatever this number is and you multiply by however many combinations that there are of that number by some unique version of whatever the rest of the key is. And so with the part numbers, we're multiplying it by 26. With the prefix, we're multiplying it by the 3-digit prefix. So the idea is that you can do the same thing with anything. So with a net ID is 8 digits, and we know that each digit, or not really digit, 8 characters, and each character can be any lowercase letter or any digit. And so total there's 36 different options for each character. So for example, for this one, we would know that the total number of combinations for each of these possible characters for the net ID would be based off of 36. So if before we were taking base 10, right? So, there was 10,000 different combinations of the 4-digit number. In this case, for each one, there's 36 different combinations, right? And so if we multiply the first one by 36 to the 5th, and then the second one by 36 to the 4th, it allows us to then get a unique integer index for any combination of these 36 characters. And so we can kind of work it out, and in the end, this particular net ID mkim16 would get mapped to the index at like 742 million. And this kind of approach is the exact same approach we're taking with the binning, and will always give us a unique index. So what would be, in this particular case, the hash size required if we wanted to use this approach of binning for something as simple as a net ID? Well, that would be 36 to the 8th, right? Because we're doing each of them all the way up to 8. This one was only a 6-digit net ID, so we didn't have to go that far, but in general that's how much it would be. And so that is just like a really giant number. So you can't have a hash table that big, so this kind of binning perfect hash function, it only takes you so far, and there's lots of cases where it's not possible, and you really do need to reduce the size of your array for this to be practical. So a good rule of thumb is that having a hash table that's 10% full is like a pretty good way to go. So if you had 35,000 active students, then you'd need to have a hash table that was 10 times bigger than that. And then you can just use a mod, to decrease it, and decrease it by whatever n that you found that you needed. And then again, anytime you use mod, you will have collisions, and so you need to come up with a way to deal with collisions. So kind of over the past couple of videos, you kind of have a sense of how hash tables work and how to write hash functions, and how to write perfect hash functions, but how perfect hash functions can result in hash tables that are too big, and so it's a balance. And so what we're going to be talking about in the remaining videos for this week is how to deal with collisions. And so keep in mind that that's just part of the design of hash tables, is to handle collisions, but you just want to minimize them. All right. That's it. See ya.